Good morning, ladies and gentlemen. Welcome to a video on applying the binomial probability theory to a couple of exam-style questions, or SAT-style questions. Alright, let's read the first one, and feel free here to stop and pause and read the questions before I actually go on and solve them, because I'm going to more or less dive into solving them, but reading them is incredibly important. Alright, here we have a probability distribution for a fair dice. This dice is going to be rolled 80 times. What is the probability of obtaining a 6 exactly 20 times? So what we can say here is that x is distributed binomially with 80 trials, and the probability of success is 1 in 6, where here x is equal to the number of 6s. Alright, so what we're looking for here is exactly 20 times. Now we can think of this as n, which is 80 choose 20, multiplied by probability of a 6, 20 times by the probability of not a 6, 60 times, and throw that in our calculator. Or, because these would be tech active, we would use technology, which would be here, distribution binomial point. We will want 20 successes out of 80 trials, and the probability of a success is 1 divided by 6. And we're suspecting this is going to be really very small. Execute. Alright, 0.17. 0.017. Alright, no worries. Then, what about obtaining a 6 24 times or fewer? 24 times or fewer is a tail left, which makes it easy for our calculator. So 24 times or fewer. And note here, the mark scheme. For 2 marks, you would have to state what I just erased, actually, that it's distributed binomial. Once you've got that, this is a 1 marker, 24 times or fewer is going to be distribution binomial BCD 24. Everything else stays the same. Yeah, the probability of 24 times or fewer is really very, very high. 0.999. What is the obtaining a 6 between 16 and 24 times, inclusive? Alright, so if you think about the possibilities here, we have 0 all the way up to 80. And we're looking for the probability of hitting between 16 and 24. Now we've already found that there and lower is 0.999. That's from above. If we want to hit this gap here, we'll have to do 0.999 subtract that. And that there is the probability of 15 or lower, because we want to be inclusive of 24. So that's why we're going to have to calculate the probability of getting 15 6s or fewer and subtract it off. So if we go to here, we want to change that to 15, and lots of people make the mistake of putting 16 there. Execute, execute. So the probability here will be 0.99 minus 0.748. 0.999 minus 0.748. And whatever that is, you can do it. Alright, let's say a weighted die is one where it has an unequal distribution of probabilities. There. What is the probability of rolling this dice 80 times and obtaining a 6 exactly 20 times? You'd suspect it to be slightly higher, but let's have a look. Calculator, execute, distribution, binomial, BPD. We want 20 times, and this time our probability of getting a success is 0.25. It's, well, 0.1025. Not bad. Now, that seems like a weird place to end the question. In a second, it does go on to more complicated when they add the dice distributions together. But we'll do that one later. Alright, here is a question from a past exam. First thing to note is the sheer amount of writing. In the exam, there will be worded questions, and they will take a long time to read and process. So pause me, read that a couple of times. Alright, so assuming you've got that, in this random town, where the probability of a randomly chosen person having the Ebola virus is 1%, or 0.01. Blood samples from 100 randomly chosen people are tested for the virus. What is the probability that, if pooled, the blood testing used of the sample is going to be negative? So the probability of getting all tests negative is going to be, if you want the full working, well, we need to be the success, the probability of success here, success meaning someone having the virus, which seems odd, but success is 0.01. So here, the probability of 100 people not having the virus is going to be 0.99, the probability of someone not having the virus to the power of 100. Now the rest of the binomial expansion you could fill in here, which would be C 100 to 0 successes, the probability of 100 failures multiplied by the probability of 0 successes. And that would be the full formula. We know that that goes to 1, this goes to 1, this is the real outcome we're concerned with. And it turns out that there is 0.366. Alright, hence, what is the probability that if pooled in testing, the sample will be positive? Alright, well there's two possible outcomes here. Either the sample is negative, that, or the sample is positive. The sample positive would be one take, 0.366, which is 0.3, it's that, 0.634. Okay. E, the expected number of blood tests needed to test samples from 100 randomly chosen people using pooled blood testing can be calculated by doing 1 times the probability that only one test is needed, or 101 times the probability when 101 tests are needed. So bear in mind that this here would be if only one test is needed if the sample is all negative. If the pooled sample is negative. If the pooled sample is positive, then you need to do another 100 tests to test all of those people. Use your values for part 1 and 2 to calculate the value for E. So here, it's clear you could use carry-through error, but because we've got it right, hopefully it's not carry-through error. E is equal to 1 times 0.366 plus 101 times 0.634, and the expected number of tests is 64.4. Give a reason why pooled blood testing is preferable to testing individual samples in this case. Alright, so what this is saying is here is the two possibilities are either the pooled blood test is all negative, so only one test is needed, or the pooled blood test is positive, so only 101 tests are needed. But the expected outcome for this particular probability of having a 0.01, the expected outcome is 64, which is better than the alternative of testing every individual. So if we were to test 100 individuals, the expected number of tests is 100, but using pooled tests, the expected number of tests is 64. So to give a reason here, you would have to write out a nice sentence, but essentially the sentence is going to end up saying 64.4 is less than 100, and that would be without pooled testing. Have fun reading that. Alright, show that in a large town where the probability of a randomly chosen person having the Ebola virus is 0.075, blood samples from 100 randomly chosen people are not preferable to individual testing. Alright, so here we use that expectation. It's the formula they gave us before. And note that they will give you random formulas halfway through the exam that you're then expected to understand what they're on about and use. So that's going to be 1 multiplied by the probability of the sample not being positive, or the sample being negative. So the sample not being positive is going to be 1 take 0.075 to the power of 100. That's essentially the same calculation as we did in part A, plus 101 times the probability that the sample is positive. So the probability here the sample is positive is 1 minus this thing here, 1 take 0.075 to the power of 100. And it turns out that this is equal to 100.96. So because it's equal to 100.96, that has an expected value of higher than 100, so it would be easier just to test the 100 people rather than pooling the samples, because by pooling the samples we're expecting to do 101 tests, well 100.96 tests per 100 people. Excuse me. Alright, consider the case where samples are chosen randomly for 100 people. Show that E, the expected number of blood tests needed, can be written as. Alright, where the virus is P. So this is taking the general case of what's happened before. Previously, the probability of having the virus is 0.01, and that way pooled testing was better. Then it was 0.75, individual testing was better. Now we're trying to simplify when it's just P. So just P, we would start off by using that expectation formula and knowing where it's coming from. So the expectation formula is 1 multiplied by the probability that only the pooled sample is tested, i.e. it's negative. 1 take P to the power of 100, that's all 100 people being negative, plus 101 lots of 1 minus that first probability, 1 take P to the power of 100, there. Alright, now we're asked to show that. So we're aiming for that there, that's our endpoint, so let's do some algebra to get there. Some algebra to get there, I would be expanding this right-hand portion. E equals, that 1 doesn't really need to stay, so we're just going to write it as 1 take P to the 100 plus 101 minus 101 lots of 1 take P to the 100. Alright, interestingly here, what we have is a constant term here. That 101 has no P or anything attached to it, so it's constant. And I'm going to write it at the front. The reason I'm writing at the front is because, well, they had 101 at the front. Seems logical enough to do. And then you can see that this is, well, one lot of 1 take P to 100 minus 101 lots of 1 take P to 100. So that then is minus 100 1 take P to the 100. And that's shown. And you would simply have 2 marks, one for there, one for there. Alright, hence or otherwise, find the values of P for which pooled blood testing is preferable to testing individual samples. Alright, so using our formula from above, the expected number of tests would equal to 101 minus 100, 1 take P to the 100. Now, if we've got 100 people, we would either expect to have 100 tests individually, or this is the expression for the pooled sample. And we're looking for the values of P for which this side is lower. So we want this side here to be smaller because that's the pooled testing. Find the values of P for which pooled testing is preferable. So really, I know there's an equal sign there, but we should be looking for an inequality sign like that. Alright, inequality signs are scary, I know, but we just treat them essentially like equal signs unless we multiply or divide by a negative and then we flip them. And that we should have covered previously. Alright, let's take 100 from both sides. If we take 100 from both sides, we get minus 1 is less than or equal to minus 100, 1 take P to the 100. And note your calculator could probably get you the value of P right from here. Divide both sides by negative 100, which will leave you with 1 on 100. Flip the sign. 1 take P to 100. Get rid of that 100 by taking the 100th root of it. So the 100 root, 100 root of 100th is not going to be pretty. 1 take P. Take 1 from both sides, or add P, rearrange it to get P by itself, essentially. We've lost the sign. Alright, let's do it in 2 steps. Take 1 from both sides. Then multiply both sides by negative 1. So the sign flips, we get P, and that's 1 take the 100th root of 1 on 100. then in the calculator, well, that would be the exact answer. In the calculator, it turns out that P is less than or equal to 0.045. And note, with 3 marks, you wouldn't have had to show all those algebraic steps. You could have reached for your calculator earlier than that. Alright, but that is a late exam question. By late exam, I mean it's later on in the exam. It's meant to be hard. The idea is to split the A's from the A pluses there. There's still lots of marks you can get quite cheaply, but then it does go on to a more complex modelling scenario down here. I think it's a pretty nice exam question. Alright, thank you for watching for so long.